There was a man and an ancient mathematical philosopher. His name was Archimedes, and he once challenged the king of his own empire that he can pull a ship using only his strength. Sounds impossible, right? How can an average guy pull an entire ship from the dock to the main board? It sounds impossible, but not for Archimedes. Archimedes had done all the researches required for this aspect. What he did is actually use a complicated pulley system to increase his work advantage, and finally he was able to put an entire ship from the dock and connect it to the harbor. It sounds impossible in the first glance, but it is possible. Nowadays, every car winch which is found in recovery vehicles uses some kind of the pulley. Gear ratios are the simple tactics used in pulleys which actually reduces the amount of force required and increases the distance of consideration. For example, if I have a ant, for example, and at one side I have an entire big elephant. So what I do is, you can imagine, right? Elephant will easily pull out an ant because it's just nonsense, because an ant doesn't weigh at all, whereas an elephant weighs around a ton. So what will happen, the ant will be moving with the speed of the actual elephant. But what I can do is put a hard gear ratio if I reduce friction or neglect it, because friction reduces the efficiency of any system. What we observe is that the ant is able to move that elephant using a high gear ratio. But the condition applied is that the ant has to travel around a kilometer to move the elephant an inch. That is because the force has been doubled, but the distance you have to travel have been reduced to half. Let's take another example. You know winches, right? The thing that we have on off-road vehicles at the front. Well, they are used so that you could pull out your car yourself, so that you don't require any external forces. You know that an electric motor doesn't have the power to accumulate such a big vehicle. What we do here? We use a simple pulley mechanism to increase the gear ratio. Now what we have to do is rapidly pull that rope, which rapidly pulling increases the speed, and until it gets to the another point, that speed is converted to force energy. We have learned it, right? If we have a simple, fulcrum seesaw type thing, we know that they are called levers. We have studied it so far, right? That we know that from the distance from the load point to the fulcrum is known as load up, and the point where the effort is applied and the fulcrum, the part between them is known as the effort arm. We know that as the effort arm increases, it is known as a force multiplier. Because what we are doing, if we apply an effort of around 1 meter from this side, the object may go only for a short quarter mile. But we notice that it goes up with a pretty larger force, even larger than the thing that we actually pushed forward. Just oppositing the scenario, we notice that reducing the arm or the effort arm, we notice that it actually creates it's a speed multiplier, because when you move an inch, that will move around 3 to 4 inches, and that's only because what you are doing is actually giving the aspect of that whole length is same, and when you move just a little bit here, the more distance is covered. But the conditions is that you have to apply more force here to get the same fulcrum point from bottom to top. This is the thing, or the simple mechanics of how a pulley works. Now let's talk about a fundamental pulley. We know that fundamentally pulleys are nothing but just a simple device which changes the direction of applied force. We know that a pulley actually changes the direction of the force should be applied. For example, if you have you ever seen those wheels that are put on wells so that you could draw out water from the well? What we do here, you know that you have to pull the bucket outside in the direction upward, so the water also comes with it. But do you know that what pulleys do? Actually, they use a wheel which is easy to roll, and that's a very frictionless wheel, so no energy is lost using that friction. And another thing is that when using a circle, we actually change the tangent to where we want it. So actually now you can use your own weight and your own power to actually pull that thing, and you may also use your weight and lean backwards to get even more energy. What happened here? The amount of energy required to pull that rope and pull that bucket also has been now changed to the direction that in your hand. What now had happened? Actually talking about it, we have just changed the direction so you can lean on it and pull the bucket out. Now you can use another pulley and put that side. What will happen? Yes, the direction will change again, and changing the direction also will change the amount of force required. We can see this using a small clip. We know that when a thing is rolling, it reduces the friction. That's why it is easier to pull it using that wheel. But putting a combinations of pulley actually increases the work efficiency, as you have to pull long but with a little bit of force. But in the well, what happens is it moves very less distance but a very high amount of energy. We know that when an object spins, the power applied on that spinning object is known as torque. Samely, if the rope is also pulling, that means some energy is also getting in the rope. This energy is known as tension. Ropes always tend to be in tension because you cannot push through a rope. Have you ever seen that somebody is pushing the rope and then doing some work? Rope are designed, or according to the molecular structure of ropes, you can only pull it and then get the work done. Have you seen those cars and small toys where you pull a long thread and just get out of your hand from there? What happens is that store energy in the springs and stuff inside changes the amount of energy that you put at the starting and the end. What happens? Well, you actually pull the rope, you are actually accumulating distance as the energy in there. But now what happens? When you leave it, that distance is now converting to force and the distance reduces. Have you ever seen that a car, you pull it this much around 5 inches, but after some time when it travels, it is less than 5 inch? No, right? Because the more you pull, you have the more energy in the car. Well, the less light it is to pull that rope, the less far the car goes from the start initial point. We know that more harder it is to pull, the more stiff the spring will be, and more rapidly and more forcefully it will get out the energy to the wheels, and the car will move even longer than our starting scenario. So what did the Archimedes did actually? He just used these simple mechanisms and put them together. He used a pulley system. Well, he used a very complex pulley system. He only used around 4 to 5 pulleys and actually generated the work efficiency that he wanted to pull a ship. You know that a ship may weight around 3 to 4,000 tons, but that's not what we always see, right? Have you ever seen a ship pulled by a human directly? No, right? You have those small winches and those small ring mechanisms and those pulleys from which the combination of force generated actually pulls the thing. We know that if we have a simple diagram of a pulley, we know that if you put two of them in a series, the working efficiency or the pulling force upward is 2 times. What happens is now actually the thing is going above. Well, the thing here is that when you have that actual car and you actually pull the ship out of the main dock, you actually see that the combination of the force is generated is very high, but the distance that is traveled by the Archimedes is larger, because that larger distance is now converted to force, and then the ship is traveled a very small bit but very high force.